I'm about to talk to you about things as broadly ranging as ocean waves and sound from speakers and light out of lasers. What I need for you to understand first is that I need to be talking about monochromatic. And so that means monochromatic means one color, that's the chromo there, but chromo has something to do with frequency. So I'm saying one frequency. So we could talk about monochromatic sound, that wouldn't be unreasonable. And we could talk about ocean waves that are occurring at a certain frequency. So I want you to imagine, for instance, not only do I need monochromatic, but I also need coherent sources. So this might be the case of when I've got two different sources, coherent. That means the sources are doing the same thing at the same time. So when one source is, I don't know, a crest, then the other source also must be a crest. So that's what happens if you wire your speakers correctly and then play a mono sound through it. Mono in that sense meaning not stereo. Mono versus stereo. In stereo sound, you're getting different sound out of each speaker. That would not be coherent. We need monochromatic, absolutely one frequency, and we need mono, not stereo, so the coherent, the two speakers are doing the same thing. So here's the idea. You come in here with a kid bopping up and down in the ocean, and that kid is making waves. And if I give you a graph of the waves right here, you'd be able to say the kid's right there making waves. And I want to argue that each of these waves here is, I don't know, what do you want to call it? Let's call each of these waves a crest or a peak. So I'm going to say that each of these lines that I've drawn is a crest. And notice how if the kid's right there, then the crests are traveling out in all these directions. I'm not going to draw any. I kind of do want to draw things on here. No, I got it. Got another piece of clear, and you won't be able to tell that I'm not drawing on the same page. So here we go. This is the velocity of the wave crests. They're always going normal to the wave fronts. Okay, yep, going outward. Have we done this kind of thing before? Oh man, the math looks incredibly similar to something else we've done. So I've got these crests here, and they are going away from my source. But what if there wasn't just one kid bopping up and down? Ooh, can we define this distance here before we go on? What is that distance between there and there? What do you think? Let's call it a wavelength. Sure, that's the wave. So in between each of these crests, there must be a trough. And I could draw that as a dotted line if you want. It's right here. And it goes all the way around. So the kid's bobbing up and down, and he is making a crest right now. And he made a trough half a period ago, and of course he made a crest a full period ago. That's what defines a period, right? So let's clear away some of this nonsense and get another kid bopping up and down. And this kid bopping up and down is also, look at him, he's also making a crest at that same instant. And let's say that they're very near each other. If they are very near each other, like really near each other, like right now, I need another one of these sheets. If they're very near each other, dang it, wait right there. Don't go anywhere. I've got another sheet on top of this. So what I've got is a source right here. There's a source here, and there's a source here, and they're both emitting the same frequency. You can tell that it takes the same, well, we're getting the same wavelength, and these guys' waves obviously are traveling through the same medium, so they're going at the same speed. But here's my point. When there's a source here and there's a source here, I'm going to get some regions where the crest from one source, here's the crest from the top source, is overlapping with the crest from the bottom source. So right here, I've got what's called a supercrest. What about right here? Oh, it seems like we have a supercrest there, and supercrest there, and supercrest there, and supercrest kind of over here. Those ought to be in a straight line facing this direction. The cool thing about that is each of these points is exactly the same distance from one source as it is from the other source. I could define these things as like L1 and L2. That's the distance from one source and the distance from the other source. Now I'm going to do it again, but slightly differently. I want my sources to be more separated from each other. Don't worry, I came with more paper this time. And I'm going to see, well look, here's one source, and here's another source, and I'm going to separate them by a fair distance. Let's separate them by, ooh, look at that. That's separated by one wavelength. That's separated by two wavelengths. Let's separate them by, heck, 3.5 wavelengths and see what happens. All right. 2.5 wavelengths? Yeah, 2.5 wavelengths. All right, here's what I want to do. I want to study what's going on right here, and I'm going to say at this location, the distance that I can define as L1 is the same as the distance that I see as L2. The distance from one source and the distance from another source is the same. And that's true everywhere along this line. So the cool thing is that when I get crest and crest, that's constructive interference. And when I get crest and crest constructive interference, crest and crest constructive interference. But let's think about troughs. There's a trough in between these from the lower source, and there's a trough in between these from the upper source. So where I have crest and crest, I guess, oh, let's look at this location right here. I've got crest and crest here right now, but remember the waves are moving away from the source. So this wave is moving that way, and this wave right here is moving that way. So a moment later, the trough from this wave and the trough from that wave will be right here. So I'm getting super wave right here. I'm getting enormous, well, let's see, enormous bounciness, or if this were sound, I would have an enormous volume. It's not that where they're, see, I need to remind you about how your ear works. You're sitting here trying to listen to something with your funky looking ear, and the only reason you hear me talking is because you're getting waving of the sound. This is pressure as a function of time. Let's see if I can graph this. This is pressure. It's also pressure as a function of location. So as you wait, you just sit there listening to my sweet voice coming into your ears, and the pressure is changing as a function of time, and your brain decodes that into sound. Similarly, if you're looking at something, the only reason that you can see it is because the electric fields and the magnetic fields coming into your eye are changing. That's what light is, and you perceive that in an interesting way, but slightly differently. But still, it's not about whether there's a crest or whether there's a trough. It's about the pattern of crests and troughs that determines the frequency of the light that you see, and therefore whether you can see it or not, and furthermore, what color you see. With this case of sound, you do not hear high pressures. You do not hear low pressures. You hear the pattern of changing pressure coming into your ear. So if we're going to consider this location right here, this location is a loud location because it is alternately high pressure, and then as this moves through it, it'll be low pressure, and then high pressure and low pressure. All this is moving through that location, so a listener here will hear a loud sound. But what if we found a location where the crest from source 2 was overlapping with the trough from source 1. You see, this is the trough from source 1, and I wanted to overlap with the crest of source 2. Ooh, that location does exist. What about another one of those? Here's another crest from source 1 overlapping, sorry, it's a trough from source 1. This guy right here is a trough from source 1, and we've got the crest from source 2 overlapping, and here's another location where the trough from source 1 overlaps with a crest from source 2, and maybe I can get you still another location. What if I had a trough from source 2 overlapping with a crest from source 1, and a trough from source 2 overlapping with a crest from source 1. I hope you'll agree that although my picture is sloppy, there are kind of some lines right here where we have no sound at all. I can certainly agree that will be destructive interference when it's a crest on a trough, right? And a trough and a crest, and a crest on a trough, and a trough and a crest, and a crest on a trough. It is, in fact, perfectly quiet right here. There is no wave. You've got the average water level, or in the case of sound, you've got the average pressure in the room right here. If you put your ear right here, you will not hear the sound from either of the two speakers. If you put your ear right here, you'll hear twice the amplitude of sound from one of the speakers. But if you put it right here, you'll hear, well, twice the volume, twice the intensity. I don't know, go watch that other video. So this is a location of extreme quiet. I can find another location of extreme noise. That looks like crest and crest, crest and crest, crest and crest, crest. Oh, that one's way off. Yuck. Okay, crest and crest, but also trough and trough, trough and trough, trough and trough, dot, 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 trough and trough, and then trough and trough. This should also be a line. It's clearly deviating up there where I've made my circles kind of sloppily, but this line is also loud. And the cool connection that we can make, let me make another loud line. The loud line is where these guys cross. They're like cross, 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 cross. That should be a loud line. Of course, this ought to be happening over here, sorry. And then there's also a quiet line in between the two of them, right there. So you get this interesting pattern of interference, and this is called, wait for it, this is called, well, it's constructive interference here, and it's destructive interference here, and it's constructive interference. Broadly, we're starting to address an issue called diffraction. And diffraction is an extremely important physical concept because it is what happens with waves. Waves always interfere. And in fact, this guy, hi Newton, this guy famously got light completely wrong. He said, I believe that light cannot be a wave because it does not exhibit diffraction. That is, you can't get light to interfere in this way. And the only thing wrong was he didn't look close enough. There were actually instances in the 1600s that they could observe light experiencing diffraction. And now it's very easy to see. In fact, I'll show you in our classroom. But back then, he couldn't see light seeing diffraction. So we've got these alternating reasons of loud and quiet and loud and quiet and loud and quiet. And I'm going to pull this away. You can look back in the video if you want to see that picture again. But I'm going to pull it away and start to discuss a little bit why a location might be loud versus another location that is quiet. If I have a source here, I like to talk about speakers. Like, wow, that's about dead. So let's get an orange speaker right here. And we'll have it be a woofer and a mid-range and a tweeter, and it's putting out some sound. And there's this other one down here, and it's got a woofer and a mid-range and a tweeter putting out some sound. And that sound, well, if I look at a line right here, I could walk up and down on this line, and you know, of course, that everybody who stands right smack in between these two speakers is going to have the same distance from one speaker as they are from the other speaker. So I can call this location here, let's call it P, and I'm going to say that the distance from one speaker and the distance from the other speaker, we're going to call these, what, L1 and L2. If, here's my first statement, if L1 equals L2, then constructive interference. Cool? And I also want to say that if, oh, wait a second, let's get another one. Let's move to a location right here. Notice how we've gotten a little closer to one and a lot further from the other one. If this location, we could just call this Q1. You want to call that P1? Okay, sure. If L2 is L1 plus half of a wavelength. That's too complicated. Let's go to that one next. I want to do a red one, for instance. What if by the time this distance here, this is L2, by the time L2 makes it to this location, L1, oh man, what am I trying to say? I'm trying to say, like, if I did L1 on here, then this distance here, this would be L1 on L2. See it right here? I'm trying to make that the same distance right there. Then I'm saying this additional distance, what if I make this additional distance a wavelength? What if that distance right there is one wavelength? Well, if that's a wavelength, then if this guy's putting out a crest right now, let's say it was putting out a crest right there also, then this guy was putting out a crest right now, and it was putting out a crest back then, and is putting out a crest right there. That means we're going to get constructive interference again. Wait a second. So here's what I can say now. I can say if L2 minus L1, if the difference in path length is equal to a wavelength, or I guess L2 minus, you see, it's not just one wavelength, it could be 3 or 4 or any integer number of wavelengths, then constructive interference. That would be a crest from this speaker hitting this location at the same time as a crest from this speaker hits that location. Because if they're in phase and they're monochromatic, then we're going to get constructive interference. I don't care whether you're talking about ocean waves or light or sound, it's all going to be the same. What about up here? This, I'm arguing, is the difference between them. Let me write it like that. L2 minus L1 is half of a wavelength. So that means that the crest in this blue picture here, this distance right here is half a wavelength. That would be, well, there's L1, and there's L2. This distance is half a wavelength. That means that when this one was putting out the sound that reached, this one was halfway out of phase with it, which means that, oh shoot, so destructive interference. That means that a crest from this wave is hitting at the same time as a trough from this speaker right here. And that means that when the crest from this speaker hits it, we'll be on a trough from that one. Those guys appear completely out of phase, and you in fact can hear absolutely nothing. Hard to believe, but it's true. And if I give you a graph of the waves right here, you'd be able to say the kid's right there making waves. And I want to argue that each of these waves here is, I don't know, what do you want to call it? Let's call each of these waves a crest or a peak. So I'm going to say that each of these lines that I've drawn is a crest. And notice how if the kid's right there, I'm about to talk to you about things as broadly ranging as ocean waves and sound from speakers and light out of lasers. What I need for you to understand first is that I need to be talking about monochromatic. And so that means monochromatic means one color, that's the chromo there, but chromo has something to do with frequency. So I'm saying one frequency. So we could talk about monochromatic sound, that wouldn't be unreasonable. And we could talk about ocean waves that are occurring at a certain frequency. So I want you to imagine, for instance, not only do I need monochromatic, but I also need coherent sources. So this might be the case stereo. In stereo sound, you're getting different sound out of each speaker. That would not be coherent. We need monochromatic, absolutely one frequency, and we need mono, not stereo, so the coherent, the two speakers are doing the same thing. So here's the idea. You come in here with a kid bopping up and down in the ocean, and that kid is making wave of, when I've got two different sources, coherent. That means the sources are doing the same thing at the same time. So when one source is, I don't know, a crest, then the other source also must be a crest. So that's what happens if you wire your speakers correctly and then play a mono sound through it. Mono in that sense meaning not stereo. Mono versus